Hello everyone, and welcome back to another cartography lecture video. And in this lecture video, I want to move beyond what we talked about in the last video, where we talked about the 4 reasons why we generalize, and I want to move into talking about how we generalize. So just to recap what we talked about last time, we had these 4 reasons why we generalize. And we said that you have issues where features start to sort of come together and overlap. You have issues where changing one dataset causes a break in the geographic reality of another. And you have this idea of complication where as you zoom out, what was originally relevant and important detail starts to become noise. And so hopefully that was a quick refresher for you and you understand why we generalize, because now I want to move the discussion to how we generalize. And as with so many things in cartography and GIS, the answer for how we generalize really depends greatly on whether we're dealing with raster data or vector data. And with vector data, whether we're dealing with points, lines, or polygons. And so what I want to do is I actually want to break this discussion up, spend this video talking about raster data, and then spend the next couple of videos talking about vector data. So with raster data, the pretty much only choice you have for generalization is going to be something called resampling. Which is basically changing the spatial resolution. Right, so you can think of it conceptually as going from several small pixels with 3, say for example 3 meters, right, down to 1 pixel that is 6 meters, right? We've changed the spatial resolution. And this might initially seem, okay, sure, we're making the pixels, we're reducing the number of pixels to decrease the number of pixels to address the idea that we've reduced the amount of detail that we need. But the question becomes, what do we do with the pixel value? Right? What do we do with the value? Because originally, right, we had 4 different values here. We've increased the length of one side, right? We've reduced the spatial resolution, as they say. So now, what do we do with the value, right? What do we put in this pixel? And this is where resampling becomes a little bit more complicated and we need to have a discussion, right? Because there's a lot of different options that we could take. And so what I want to do is I want to try to diagram out, at the very least, one of the options so that you have an idea conceptually of what's going on behind the scenes. Right? So basically what we have 4 options. We have 4 resampling options. Right? For what to do with the pixel value. The first is what's called nearest neighbor. The second is what's called bilinear interpolation. The third is called cubic convolution. And the fourth is normally referred to as majority You might see it called some other things, but essentially it's just a majority. And so let's give ourselves a little bit of room. And before we talk about what each one of these does, I want to draw a diagram to sort of help explain it. So let's say that we have, right, a raster image, something like this. And for convenience sake, I'm going to give them pixel values equal to their sort of position in this array. So 1, 2, 3, 4, 5, 6, and so on. And let's say that these are this original image was 3 meters per side. So that means the length of one side of this square was 3 meters. And let's say that we resample, let's say we resample to 5 meters, right? So we've decreased the spatial resolution, so we now have fewer pixels, right? We've reduced the detail or the data resolution. And so if we kept the same corner, right, we would go something, you might have something that looks like that. Right? This red box here, right, this is our new pixel. So the question becomes, well, what do we do for the pixel value in here? Well, the first option was nearest neighbor. And the way that nearest neighbor tries to address this issue is by saying, well, what is the pixel value of the pixel that is closest to the center of the new pixel? Of the closest old pixel. Right, so what does that mean? Well, let's go ahead and for the ease of diagramming here, let's bust this piece out here, and so we can make it a little bit bigger. So we might have something that looks like this. So this is going to be 1, 2, 5, and 6, right? These 4 pixels are these 4 pixels. And our new pixel is going to look something like this, right? So basically what nearest neighbor is going to do symbolically is it's going to say, okay, the centroid of this pixel is here. This is the well, actually, it's a different color, right? The green dot is the center of the pixel. Right, so this is going to have a center, this is going to have a center, and this is going to have a center, right? We are also going to have the new pixel is going to have a center. And basically what nearest neighbor does is it looks at the distance between, right, the centers of all of the old pixels and the center of the new pixel, and it says, well, which one of these is the closest, and that is the value that we're going to assign to the new pixel. Right, so it's going to look at this distance, right, this distance, and this distance, and it's going to say, well, which one of these is the shortest? So in this case, it's going to go with this, right, this distance here is the shortest, so it's going to assign this new pixel a value of 1. Right? So in our nearest neighbor approach, right, this pixel is going to get a value of 1. Put this in parentheses here. This is going to get a value of 1. Okay. So bilinear interpolation, right, rather than just using a single pixel value, it's going to take the average of the 4 nearest pixels. Right, bilinear interpolation is going to take the average of the 4 nearest pixels. Right, so in this case, right, it's going to be the same 4 pixels that it's considering, but rather than just picking the nearest, it's going to take the average. So if we took the average of this, right, that's going to be 1 plus 2 is 3, plus 5 is 8, plus 6 is 14. It's going to be 14 divided by 4, right? So let's make a note here. Right, 14 divided by 4, which is going to be approximately 3.5. Right, so you can see how going from nearest neighbor to bilinear interpolation, right, we've already had a drastic change in the pixel value. Nearest neighbor would have picked 1, bilinear interpolation would have picked 3.5. So cubic convolution does the same thing as bilinear interpolation, except instead of taking the nearest 4, cubic convolution takes the nearest 16. Right, 16 nearest pixels. So I'm not going to bother doing the math, but you can imagine how we could take the same approach but add more pixels to get a different average. And then finally, majority. Majority basically uses the value that occurs the most among the pixels in the whatever size you pick. Right, so bilinear interpolation specifically 4, cubic convolution specifically 16. Right, majority uses the value that appears the most for a given number of pixels. Right, so you could specify 4 or 16 or 32 or whatever. It'll look at that number of pixels and it will take the value that appears the most. So hopefully you understand conceptually what these 4 approaches do and how you can end up with a different value depending on which one you pick. So now the question becomes, well, which one do I choose? Right? How do you choose? How do you choose a resampling option? So basically, nearest neighbor when you don't want to change pixel values. Right, when the actual values in the pixels mean something and you don't want to change them. So typically you're going to use nearest neighbor when your pixel values are something categorical, like say land cover classes. And so a value of 1 might mean forest and a value of 3 might mean water, right? Taking the average to get, 2.5 would not mean anything. So you would want to use nearest neighbor whenever you don't want to change pixel values. Because bilinear interpolation and cubic convolution both take the average, you're generally going to want to stick with bilinear interpolation unless you really want to smooth out sharp values in your image. Right, so cubic convolution will smooth extreme data values. In your image. So bilinear interpolation is generally an acceptable option most of the time, unless you know you don't want to change your pixel values or you have a lot of extreme data that you really want to smooth. Majority is good if you are dealing with categorical data and you want to take into account maybe if you have a lot of pixels occurring, like if you've done a pretty massive resampling, like gone from say 3 meters to 30 meters, and you might have 100 pixels that you might want to work with, then majority might work. All right, you use majority if you have categorical data. Right, so this again could be land cover type is typically the best example of categorical data. And you have, it's supposed to say drastically. Changed resolution. Right, so to sort of put that in perspective, right, in this we went from 3 meters to 5 meters, so we were really only considering at most 4 pixels, so majority didn't make a whole lot of sense. But imagine if we went from 3 meters to 30 meters and we're encompassing, more pixels than we've even shown here. It might not make sense to just pick the value from 1 pixel, but averaging still wouldn't make sense. You might want to go with a majority in that case. So again, use nearest neighbor if you don't want to change the pixel value. Use majority if you have categorical data and you're covering a large resampling exchange. And then use cubic convolution if you know you're trying to smooth out extreme values. I know this was a slightly longer video. I hope this all made sense. And as always, if you have any questions, please reach out. Thank you.